Welcome to the course on advanced machining processes. Today we are going to discuss on a mechanical type advanced finishing process that is called magnetic abrasive finishing process. So there are different kinds of conventional finishing process, whatever we have heard, like grinding, honing, lapping operation. Okay. But all these grinding, honing, lapping operation, it is very difficult to control the forces, finishing forces. But in case of this non-conventional machining or finishing forces, you can control the finishing forces by using a magnetic field, like in magnetic abrasive finishing process. So that's why when you are trying to automate the process by using any automate the process, okay, so these conventional finishing processes are very difficult to control finishing forces, but non-conventional finishing forces, by using this magnetic field you can control the finishing forces. Okay, so one more thing is that this adaptability of the polishing media. Like when you are using grinding wheel, at that time you cannot polish any kind of complex freeform surface. But by using this magnetic abrasive finishing, so this magnetic abrasive finishing process, you can polish any kind of complex freeform surfaces. Okay. Generally by this magnetic abrasive finishing process, generally cylindrical and flat workpieces are polished, but any kind of complex freeform surface also can be polished by this magnetic abrasive finishing process by using a suitable fixture. Okay, so in MAF process, use of controllable magnetic field to direct the brush to adapt the contour of the workpiece surface to be finished, and nature of the brush is flexible. Okay, so whatever we told, that flexible means it can polish any kind of complex freeform surface because of this flexible brush. So this nature of the brush is flexible to access the surface where the conventional tools are hardly applicable. Okay, inside the pipes or bentings. Okay, like you want to polish at the internal surface of a tube. So any kind of conventional polishing process is difficult to polish at the internal surface of the tube or in any inaccessible areas. So in those inaccessible areas, a magnetic abrasive finishing process can be used to polish. So what is the working principle? So working principle is that workpiece is kept in between the two poles of the magnet. Okay, cutting force is controlled by the magnetic field generated by an electromagnet, or you can use permanent magnet also. So nowadays very high strength permanent magnets are available, like neodymium iron boron. So using this permanent magnet with highest grade, you can get up to 0.6 Tesla magnetic field. Okay, so you can use electromagnet or you can use permanent magnet. The advantage of this electromagnet is that by changing the current to this electromagnet, you can change the magnetic field, which is not possible by in case of permanent magnets. Okay, so these magnetic abrasive particles join each other and form a flexible magnetic abrasive brush, which behaves such as a multi-point cutting tool, and then finishing is done by creating relative motion between this workpiece surface and flexible magnetic abrasive brush. So this is the magnet here. So this is the magnet here. You can see this is the so you can see this is the magnet here. So this is the north pole of this magnet, and here you can see this we have used here it is used a magnetic base material. Okay, so because we have used this north pole here, and then this is the magnetic base plate here, and this is our workpiece that has to be polished, flat workpiece surface that has to be polished, and in between this north pole and this workpiece, these magnetic flexible magnetic abrasive particles are kept. Okay, so these flexible magnetic abrasive particles are actually iron particles. These are 99.9% pure iron particles, and abrasive particles are mixed with these iron particles, and they are made a homogeneous mixture. Okay, so some binding material like binding fluid, like some grinding fluid, actually it is mixed for binding these abrasive particles with the iron particles. Okay, so when you are applying some magnetic field, what happens? These magnetic abrasive particles, actually it will form chains along the lines, magnetic lines of force. So this is the magnetic lines of force. Along this magnetic lines of force, these magnetic abrasive particles will form the chains. Okay, so these abrasive particles are actually held in between these chains. Okay, so these abrasive particles are held in between these chains, and these lines are magnetic equipotential lines. Okay, so these lines are magnetic equipotential line, are perpendicular to that. These lines are actually magnetic field lines. Okay, so these abrasive particles will form chains along this magnetic along the line of magnetic force. Okay, so these abrasive particles are held in between these magnetic particles, and it will form a flexible magnetic abrasive brush. Okay, so it will become a very solid kind of thing, and it will form a flexible magnetic abrasive brush. Okay, so it is very hard also. Now we are giving a rotating motion to give a relative motion between this tool and the workpiece surface. Okay, so when you are giving a rotating motion here, rotating motion of this magnet, okay, so this flexible magnetic abrasive brush also it will rotate along with the magnet, and because of this relative motion between these abrasive particles and this workpiece surface, there is a machining these abrasive particles will remove the surface undulations from the workpiece surface. Okay, so there are two kinds of forces are there. One is the normal force here, because of this squeezing of this tool into the workpiece surface through this magnetic abrasive particles. So there is a normal force is there. Okay, so this normal force will help into the penetrating these abrasive particles into the workpiece surface. Okay, into the surface undulations, and this tangential, because of this relative motion between this tool between this abrasive particle onto the workpiece surface on a fixed workpiece surface, because of this relative motion, okay, so there is a tangential force will generate. So because of this tangential force, this whatever abrasive particle indented into the workpiece surface, it will remove the surface undulations from the workpiece surface. So this working principle is very simple. So here unbonded type magnetic abrasive particles are used. There are two types of magnetic abrasive particles. One is unbonded type, and another one is the bonded type. So unbonded type, loose magnetic particles and loose abrasive particles are homogeneously mixed using a binding material, binding fluid. Generally it is a grinding fluid. Okay, so we shall discuss all these kind of bonded and unbonded magnetic abrasive particles later. And finishing is done by creating a relative motion between this workpiece surface and the flexible magnetic abrasive brush. So this is the flexible magnetic abrasive brush. So you can see here one individual abrasive particle, it is indented into the workpiece surface because of this normal force. Because of this tangential force, it will remove the surface undulations from the workpiece surface. So here you can see this is the bonded type magnetic abrasive particles. Okay, so in this bonded type magnetic abrasive particles, there is a lump magnetic particle is there, which is around 200 to 300 micron. Okay, so and there is a small diamond abrasive particles are there, which diameter is small d, and bigger size diameter is the capital D is the diameter of the magnetic particles, and small these are the small diamond abrasive particles are there. So these we having small d diameter. Okay, so these small abrasive particles are actually sintered into the bigger size ferromagnetic particle by a sintering process. Okay, so now this will act as a flexible magnetic abrasive particle. So this is a total magnetic abrasive particles. But in this case, in this figure, magnetic particles, ferromagnetic particles and abrasive particles, they are homogeneously mixed. They are not sintered here. So in bonded type, these abrasive particles are sintered into a bigger size ferromagnetic particle, and unbonded type, they are not sintered. They are separate. Okay, so there are different configurations of magnetic abrasive finishing process, different configurations. Already I told that either cylindrical workpieces or flat workpieces are generally polished by magnetic abrasive finishing process. Suppose if we take a cylindrical workpiece here, okay, so this is the north pole, and north pole, this shape actually it is some hemispherical shape is considered to generate a uniform magnetic field on the workpiece surface. Okay, so now you can see these are the these lines are magnetic lines of magnetic force. Okay, so these lines are magnetic force lines, and perpendicular to that magnetic equipotential lines are there. So these lines are magnetic equipotential lines. Now this is the north pole of this magnet, and this is our workpiece. Now to give the rotating motion, okay, so this workpiece is now rotated with a high RPM, okay, with a certain RPM it is rotated. Now in between this north pole and workpiece, these magnetic abrasive particles are actually kept. And when this magnetic field is applied in between this north pole and between this workpiece, because of this magnetic application of magnetic field, these iron particles, it will form with chains and other magnetic lines of force. It will create a pressure, normal pressure into the workpiece surface. So which is shown here. So it will create a pressure P into the workpiece surface. Okay, so because of this relative motion between this workpiece with respect to the magnetic particles, okay, so it will remove the surface undulation from the workpiece surface. So now if we consider a magnetic particle here, magnetic abrasive particle is here. So there are two forces are here. One force is Fx, which is tangent to this along the tangent to the line of magnetic force lines. And another force is that is called actually Fy. Okay, so these are the two components are there. So because of this Fx, it will indent into the workpiece surface, it will penetrate this magnetic abrasive particle, it will penetrate into the workpiece surface, and because of this Fy, this force, okay, so it will do the surface undulations from the workpiece surface. So this is another configuration here. North pole and south pole actually kept perpendicular to the north pole of the magnet and south pole of the magnet. They are kept perpendicular to each other. Okay, so this is here in this case, this is the magnetic force lines, and these are the magnetic equipotential lines. Okay, there are another configurations also there. So here in this configuration, flat workpieces are kept, okay, are polished here. So this is the north pole of this magnet, and this workpiece here this workpiece is actually magnetic workpiece. So that's why south pole is generated into the workpiece surface, and in between this north pole and south pole we have kept this magnetic abrasive particles. Okay, and this total workpiece actually it is given X and Y. This movement is given to polish the entire workpiece surface. And also at the same time this magnet also it is rotated with a certain RPM to give the relative motion between the abrasive particles with the workpiece surface. Okay, so this is another configuration of the magnetic abrasive finishing process. Here cylindrical workpiece is actually polished. Here this is the south pole and this is the north pole of the magnet, and this is the workpiece. It is rotated with a certain RPM. Okay, so these are the magnetic abrasive particles are there. There are another configuration here. Electromagnet, you can see north pole and south pole, they are perpendicular to each other. So here you can see, here we are polishing external surface of this workpiece. Here also external surface of this cylindrical workpiece we are polishing. And this kind of workpiece polishing magnetic abrasive finishing process, you can retrofit into a lathe machine. Okay, so a lathe machine can be converted into a magnetic abrasive polishing machine by fixing this workpiece into the tailstock and headstock, and another arrangement for fixing the magnets. Okay, so in this configuration you can see this internal surface of this cylinder actually polished by this magnetic abrasive finishing process. Here also it is rotated. This workpiece is rotated with a certain RPM, and this north pole and south pole are fixed here. Okay, so there are different other configurations are there. Here 4 magnets are kept just outside this workpiece. These are the work are done by Shinmura et al. Here ceramic pipes are actually polished. Internal surface of the ceramic pipes are polished. Here also you can see North Pole and South Pole, these are perpendicular to each other. Okay, so here this yoke is connected to increase the magnetic field here, and this total yoke along with these magnets, permanent magnets, actually it is rotated. So here in this case permanent magnets are used, in earlier case electromagnets are used. So these ceramic pipes, internal surface of the ceramic pipes are polished by this magnetic abrasive finishing process. Okay, so why rotation of these abrasive particles in the brush? So rotation is important to give the relative motion between these abrasive particles, magnetic abrasive particles into the workpiece. Okay, so without this rotation there would not be any tangential force. So normal force is there. So this normal force is required for this indentation or penetration into the workpiece surface, and because of this rotational motion, there is a tangential force will be generated. This tangential force is required for cutting the surface undulations. Okay, so force required to remove the material, where shear tau is the shear stress of this workpiece material, and AP is the projected area of penetration into the workpiece surface. Projected area of the abrasive particles into the workpiece surface because of this normal indentation force. So this projected area multiplied by the shear stress will give the force, required force for this polishing to take place. Okay, so now when this required force is equal to the tangential force because of this rotation, so then equilibrium condition will occur. So this finishing is about to start. But when this force, tangential force is greater than your required force, required shear force, so in that case your shearing action will take place, or your cutting action will take place, or material removal will take place. But when this required force is greater than the tangential force, or tangential force, applied tangential force is less than the required force, in that case no cutting action will take place. Okay, so these are the three different conditions are there. So this is the experimental setup available at IIT Kanpur. So you can see here, this is the tool rotation system. There are two VFD, variable frequency drives are used, and two motors are used. So here one motor is to rotate this shaft here. This shaft is connected to this magnet. So this magnet shaft is rotated here, and another motor is actually to give this X movement of this tool. Okay, to give the X movement of this tool, this another motor is used here. So this wheel is actually used for maintaining the gap between this tool, between the magnet and the workpiece. So there is a timing belt is used so that there should not be any delay or any friction between this shaft and the motor shaft. And this is the spindle. The slip ring is used to give the current to this motor, to give the current to this electromagnet. And there is a dynamometer, fabricated dynamometer, custom made dynamometer is used. Okay, so to calculate the normal force and the tangential cutting force, and there is a data acquisition system is used for measuring this cutting force and our normal force and the tangential force. So these are the ferromagnetic particles, iron particles of mesh 300 mesh size, and these are the abrasive silicon particles, silicon carbide abrasive particles. So these are the silicon carbide abrasive particles with 600 mesh size. So types of magnetic abrasive particles already I have shown. So this is your bonded type magnetic abrasive particles are here, unbonded type magnetic abrasive particles. Here this in unbonded type, these abrasive particles and magnetic particles are homogeneously mixed by grinding oil. So what are the unique advantages of this magnetic abrasive finishing process? Self-adaptability is one of the advantages. Self-adaptability means you can polish any kind of complex free-form surface. It will take this magnetic abrasive particles manganese abrasive fluid will take the shape of the surface to be polished. So that's why it is called self-adaptability is the controllability. So the strength of this bonding material or strength of this magnetic abrasive particles, bonding strength of these magnetic abrasive particles are controlled by magnetic force. So by changing current to this electromagnet, your strength of this bonding materials or magnetic abrasive particles can be changed. So easy controllability, surface finish up to the nanometer level. From this process you can get the surface finish up to the nanometer level. Very little or no surface damage. There is very less surface damage because whatever heat is generated, it is very less in case of magnetic abrasive finishing process. Surface defects like scratches, hard spots, ley lines and tool marks can be removed by this process, and these devices can easily be mounted or on conventional milling machine without the need of the high capital investment. So any kind of milling machine or grinding machine or lathe machine can be converted into a magnetic abrasive finishing process. So this process actually it is started from USA, okay, but most of the work has been done in USSR, so in Soviet Russia, okay, most of the work is done there. After that, in Japan, many researchers actually contributed into this magnetic abrasive finishing process. Okay, so these are the applications of this magnetic abrasive finishing. Cylindrical or flat workpieces can be polished. Finishing of external or internal surface of these tubes, bearings, automatic components like this can be polished. These are the crankshafts, bearings and shafts. External or internal surface of the shafts can be polished by this process. Another things are there, deburring, precision rounding of the workpiece edges, and polishing and removal of the thin oxide films from the high-speed rotating shafts can be done by this magnetic abrasive finishing process. So method of energizing flexible magnetic abrasive finishing in present investigation, there are two types of magnetic abrasive finishing. In one case constant DC current is used, so that is called direct current magnetic abrasive finishing process. Okay, so there static magnetic abrasive brass is static flexible magnetic abrasive brass is generated. But in another case pulsating DC current are used, so that is called pulsating current magnetic abrasive finishing process, pulsating DC current magnetic abrasive finishing process, or pulsating flexible magnetic abrasive brass. So working principle, so work gap is maintained less than 1 millimeter filled. So this working gap between this magnet and workpiece is filled with abrasive particles, forms the flexible magnetic abrasive brass in between this tool and workpiece, and multiple cutting tool are used. Okay, so you can see this one here, this permanent magnet is used, and here electromagnet is used. In this electromagnet, at the center this is the north pole, and at the south, at the end is the south pole. Okay, so here this is the coil, two coils are used for this kind of magnet. So here you can see this is the magnet here, electromagnet here, and this is the workpiece here, and in between this workpiece and then electromagnet. So this is the workpiece and this is the electromagnet. Here flexible magnetic abrasive particles are actually kept. So photograph of this flexible magnetic abrasive brass and required working gap, ring dynamometer. So this is the ring type dynamometer which are used. Strain gauge type dynamometer is used for measuring the normal force and tangential force. This is the workpiece fixture and electromagnet. So these are the instruments required for analysis and for the during machining of magnetic abrasive finishing process. Like sharp analyzer is used for measurement of the surface roughness, electronic balance for measuring the initial workpiece weight. Optical microscope is used for seeing the top surface of this or surface topography of the workpiece. Scanning electron microscope and atomic force microscopes are used for seeing the uh, surface profile. DC power supply is used for the electromagnet. Pulse power supply also used from the for the electromagnet. Okay, so digital oscilloscope is used to record the pulse, current and voltage. Gauss meter is used actually to measure the magnetic field in the machining zone, and ultrasonic cleaner is used for cleaning the workpiece. So measurement of magnetic flux density. So in here this is the Gauss wall probe of this Gauss meter. Here it is kept in between this tool and the workpiece. So this is the workpiece here, this is the tool here. In between this tool and workpiece, this Gauss meter is used. So it's the excited view or schematic view. Okay, so this is the hall probe of this Gauss meter, and this is the finishing zone here. It is used for measuring the magnetic field. So here you can see with the increase in the current, okay, from the center to the outer periphery of this electromagnet, from the center to the outer periphery of this electromagnet, okay, how this magnetic field is varying with the increase in the current. So with the lower current you can see here magnetic field flux density is less. With the higher current you can see magnetic flux density is more. So with the current, with the increasing current you can see the magnetic flux density is increasing at a certain point here. Okay, then with the different gap, okay, so different magnetic flux density is used. So when your gap is less, then magnetic flux density will be high. When gap is more, your magnetic flux density will be less. So this is the experimental procedure. Prepare the fresh powder for the experiment. Leveling is done using a dial gauge. So it is 1 millimeter gap is maintained. Set the machining gap using a slip gauge. Record the table position. Move the table downward. Spray powder by brass spoon in between this magnet and the workpiece. And then move the table toward the predefined value of the machining gap. Rotate the electromagnet till the finishing time. Stop the process and move the downward the table and clean the sprayed powder and clean the workpiece and measure the surface roughness and surface roughness using surf analyzer and others SEM and FEM analysis. Force measurement. So this force measurement, there are two forces are there. One is the normal force, another one is the tangential cutting force. So this tangential cutting force is responsible for the cutting operation. So two sets of 8 strain gauges. How these strain gauges are helpful? Okay. So these normal forces, this is the ring type strain gauge. This for calculating normal forces. So this one and this one, these two strain gauges are used. So at the top surface, at the bottom surface also, another 2 strain gauges are used. Okay, so for calculating the normal force, and for this tangential force at the side of this rod, at this side actually, at the side of this rod, strain gauges are attached for calculating the tangential forces. So what are the forces are here? You can see FMM is the normal force acting on the workpiece, and only one single abrasive particle is shown. And FMT is the tangential force. FMT is the tangential force which is acting on the abrasive particles. Okay, so the sensors, from sensor signals are coming signal conditioner, then data acquisition system, PC, and then data storage and virtual instrumentation software lab view. So from there actually your force is actually measured. So recording of the forces, you can see FMN. So this is the normal force which is higher than your cutting force here. So normal force is higher than the cutting force here. So it is for 0.63 ampere current. and for 0.75 ampere current you can see your normal force also increases. Okay, so it is around 100, but cutting force it is also increasing for 0.75 Tesla magnetic field. So magnetic force shows about its average value, and this is due to the irregular jumping or rolling of the abrasive in the flexible magnetic abrasive brush near the machining zone. Experimentation using static flexible magnetic abrasive brush. Preliminary experiment. So what are the responses we have calculated? Decrease in RA, initial RA minus final RA. Then percentage change in RA is initial RA minus final RA by final RA, surface roughness multiplied by 100. Okay, so metal removal rate, so whatever weight loss is there, which is used as a metal removal rate. So about 250 RPM splashing of silicon carbide particles are observed, about 250 RPM of this magnet, and observed number of magnetic abrasive finishing below, observed number of abrasive finishing below current 0.5 ampere. Observe no magnetic abrasive finishing action beyond 2.25 millimeters. Okay, so beyond 2.25 millimeter gap. So when the gap is more than 2.25 millimeter, okay, so there is no magnetic abrasive finishing. Okay, the finishing operation is usually done at flux density more than 0.1 Tesla. So these are the parametric results for magnetic abrasive finishing process. So this with the increase in the magnetic flux density, you can see magnetic abrasive pressure also increases. Okay, so this magnetic abrasive pressure increases with the increase in the magnetic abrasive flux density. Here also you can see mixing weight ratio. Okay, mixing weight ratio increases with increase in the meshing depth, increases with the increase in the meshing weight percentage of iron particles. Okay, so finishing time, you can see that with the increase in the finishing time, initially this finishing rate is very high, and then after that it is almost actually it is almost stalled here. Okay, so what happens actually, these surface undulations are actually this kind of triangular shape. When these abrasive particles are actually cutting the surface undulations here, after that this shape of this triangular peaks become plateau. Okay, so it requires actually higher force to cut this plateau, bigger size plateau. Okay, so that's why initially the surface roughness actually improves, roughness improvement is very high, but later actually because of this bigger size plateau, this removal rate, finishing rate actually reduces with time. So radius decrease, radius of the workpiece decreases with the finishing time. So radius. Okay, so there are two types of abrasive particles we told. One is the unbonded type and another one is the bonded type. So bonded type abrasive particles, it gives higher surface finish, but in bonded type abrasive particles, their metal removal rate is actually less. Okay, so for bonded type abrasive particles, your surface roughness is good, surface finish is good, but their metal removal rate is less. But in unbonded type abrasive particles, their surface roughness is very high, but their metal removal rate also high. Okay, so unbonded type magnetic abrasive particles are used for higher metal removal rate, and bonded type magnetic abrasive particles are used for getting higher surface finish. So when magnetic flux density increases, then your meshing depth also increases. Okay, so if magnetic flux density increases, these abrasive particles, iron particles are actually will make strong chains, and abrasive particles will be held with a higher force. So with the increase in the finishing time, you can see here surface roughness also reduces. Okay, here you can see that initially this surface finish started on a grinded workpiece with of 0.49 micron workpiece surface roughness. Okay, so after that the flexible magnetic abrasive finishing process is carried out on the same workpiece. Now surface roughness is reduced to 0.28 micron. Then after that, after this magnetic abrasive finishing process for a 0.88 ampere magnetic field, okay, so you can see that surface roughness is further improved up to 0.25 micron. Okay, so now at 1 ampere current you can see surface roughness is further improved, so here it is 0.22 micron. But here all the surface roughness improvements are there, but here you can see that these grinding grinding marks are not permanently removed here. Okay, so these are the AFM results, atomic force microscope results. So I told that these grinded workpiece, they have a triangular cross section. Here you can see this kind of triangular cross section of this grinded workpiece. Okay, so this grinded workpiece, when it is polished by static flexible magnetic abrasive finishing process, the surface undulations you can see here, it is removed. Okay, so now when it is this machining is carried out or finishing is carried out for a longer time, you can see the surface undulations almost removed here. Okay, so analysis of magnetic abrasive finishing process. So I told that if you keep this magnetic abrasive particles in between this magnet and the workpiece, there is a magnetic pressure actually generated on the workpiece surface. So how to calculate the pressure? So this machining pressure between the abrasive particles and the workpiece, machining pressure by the abrasive particles, magnetic abrasive particles on the workpiece surface can be calculated as P, this is the machining pressure, is mu0 Hs square by 4 3 pi mu r minus 1 into W 1 by divided by 3 into 2 plus mu r plus mu r minus 1 into W. Okay, so here in this case mu0 is the permeability of air, mu r is the relative permeability of this workpiece material, and Ha is the applied magnetic field. Okay, and W is the volume ratio of iron in the magnetic abrasive particles. Volume ratio of iron in the magnetic abrasive particles. Now stock removal can be calculated as M with the time t equal to del m into n into capital N. Here small n is the number of cutting edges of magnetic abrasive particles simultaneously acting on the surface. Capital N is the number of active magnetic abrasive particles, and volume of material removed by an edge in time t is calculated as del f by SW pi tan theta into 1 minus RA by RA0 into V into T. So del F is the force acting on the grain edge, SW is the workpiece for hardness, and theta is the mean angle of asperity of the abrasive cutting edge, and RA is the final surface roughness, and RA0 is the initial surface roughness, and V is the speed of magnetic abrasive particles, and it is the T is the machining time. So here, after putting all these values, okay, so you can get the final surface roughness in terms of this initial surface roughness. C1 is the constant here, and then LW is the machine length, and C1 is the constant. So using this above model, surface roughness and stock removal in internal surface have been computed, and comparison of computed and experimental results are found satisfactory. So experimentation using pulsating current, flexible magnetic abrasive brush. So you can see here, so here current actually, so this kind of pulsating current we are using. Okay, so these pulsating currents are actually helpful for proper mixing of these abrasive and iron particles. So it helps in proper mixing of these abrasive particles and iron particles. Otherwise, whatever abrasive particles are there at the external periphery, okay, So it will be the same abrasive particles will be there will not be any change. Okay, so for machining to take place, we need more active abrasive particles which are taking part into the polishing action. So that's why if we use flexible magnetic abrasive brass, so as the current actually it is reducing and then it is jumping, again it is reducing, it is jumping again. Okay, so during this off time of this pulse, okay, so there is a chances that this magnetic and abrasive particles, okay, it will properly homogeneously mix, and during this on time it will do the polishing action. So in this way we can increase the machining efficiency of this flexible magnetic abrasive finishing process. So comparison of surface produced by static flexible magnetic abrasive finishing and pulsating current magnetic abrasive finishing process. So here some peaks are actually available at different locations due to the non-homogeneity of ultrasonic magnetic abrasive particles. Okay, unbonded magnetic abrasive particles. So time taken in static flexible magnetic abrasive brass is 3 times than the time taken by pulsating current flexible magnetic abrasive brass. So here we can see steel grinding marks are actually visible. Okay, so by using this static magnetic abrasive brass, but here this is done. This is done actually by using this pulsating current magnetic abrasive brass. Here you can see this grinding marks almost gone. Okay, so you can expect better surface finish by this pulsating current magnetic abrasive finishing process. Okay, thank you.